Hello everyone. So today in this video we will be talking about trigonometry. I'm planning this as a multi-part series on the fundamentals of trigonometry, and this will be particularly useful for mathematical Olympiads such as IOQM in India, IOQM INMO. It's also useful for AMC 10 and 12 and ISI-CMI entrances. So in this first part of this multi-part lecture series, we will talk about the motivation of trigonometric functions. Maybe you know this. The first systematic study of trigonometric functions originated in India in the work of Aryabhatta, and we will talk about why Aryabhatta was interested in such functions. So the main question is this, that motivated all of the subsequent work, is how to compare arc length to chord length. This is the fundamental question that we are interested in. Let me explain. Suppose there is a circle. Suppose there is a circle of radius 1. Then one of the questions that even the Greeks considered is what is the length of the circumference? There were various methods prescribed. One of them was by Archimedes, and they found the length of the circumference to be approximately 6.28 if the radius is 1. Okay. Of course, the next question would be, instead of the entire circumference, what if we wanted to measure a part of the circumference? What if we want to calculate length of an arc? Length of an arc. Now, it is much easier to calculate the length of the chord. So, if these 2 points are A, B, it's much easier to calculate the length of the chord AB because we always have a ruler. We can calculate it. So, given the chord AB, given length of chord AB, can we estimate the length of arc AB? This was a question that was considered by the ancient mathematicians, and they found certain very interesting things. And first thing that they found, and I call it axiom of a circle. It's one of the cornerstones of trigonometry. Axiom of a circle. So what is it? Well, it's very simple. It's a property of a circle that is quite surprising, in my opinion. So if you take a circle of any radius, let's say radius r, let's say this point is A. Now from this point A, you cut another chord of radius r. So you cut another chord AB, or let's call this one A1 and this one A2, such that A1, A2 chord, this length is also r. So you do that. Next, you cut another chord, or you consider another point on the circumference. Let's call that A3, such that A2, A3 is also r. So I'm just taking chords of radius length. Whatever the length of the radius is, the chord lengths are that. Next, we do that again. A4. So the question is, how many times can we do this? How many times can we cut chords of length r, where r is the radius? Turns out that we can do this exactly 6 times. We can do this exactly 6 times. When we do the 7th time, when we do the 6th time, we come back to A1. Now pause for a second to consider what just happened. First of all, in the 6th time, we came back to A1. We did not sort of stop here at some point near A1, right? Some point A7. That didn't happen. We landed exactly on A1. We landed exactly on A1 on the 6th turn. That's surprising. The second thing that's quite awesome is that it happens in 6 times. It happens in 6th time. So it does not happen in 7th time or 5th time or 4th time or 8th time. It happens in 6th time. So the number 6 itself seems to be a very important number in the context of a circle. Now here is a challenge question. Here is a challenge question for those who know an ellipse. Suppose you have an ellipse. You know that an ellipse has two foci, A and B. So one may consider the center point of an ellipse O, the midpoint of AB. Now, suppose you take any point P1 on the circumference of the ellipse. Now you draw another line P2, another chord P2, such that P1 P2 is equals to OP1. Okay, so if you continue doing this, will you return to this initial point P1 after a certain number of iterations? Here is a challenge question that you can try and test. Does a similar thing hold for an ellipse, a non-circular ellipse? Okay. So the axiom of the circle, therefore, is this. Axiom of circle is if chord length is 1 or equal to the radius, one in a unit radius circle, or equal to radius, then you can draw 6 times to return to the initial position. So this gives us a very interesting relationship between chord length and arc length. That's the beginning of trigonometry. How? Well, let's draw a unit circle again. I mean, it will work for any circle, but I'll draw a unit circle. So let's draw a unit circle with radius, of course, 1. And let's suppose the chord length here is 1. It's given that the chord length A1, A2 is 1. Now can you answer what is the arc length? What is the arc length? So that's the table that we are interested in. Given a chord, we want to find the arc. So either we can give the exact numerical value of the arc, or we can say what part of the entire circumference is the arc. This arc. So in 6 times, I will complete one revolution. In 6 times, I complete one revolution. So these 6 chords divide the circumference into 6 equal arcs. So each part is 1/6 of total circumference, right? So this is 1/6 of circumference. That's the arc length. And if you know the arc length, an estimate of the length of the circumference, then you will get an estimate of the length of the arc. So in this case, it will be 1/6 times 6.28. 1/6 times 6.28, which is approximately 1.046. And this is the first entry of a table that Aryabhatta made. Sort of. I'm not giving the exact table, but it's the first entry that given a chord length, we just found an arc length using pure geometry, using a property of a circle. Now, if we say the chord length is 1/2, everything is happening is in unit radius circle. Unit radius circle. Okay. Now, if we say that the chord length is half, can you give me the arc length? Can you give me the arc length? So that's a question that I will throw for the audience. You can put it in the comment section. Thank you for watching this video. In the next video, we will talk about in more detail the trig functions. This was just the motivation. I hope you liked it and continue watching it for the next parts. Thank you, and keep on doing great mathematics.